Okay, then I'm starting. So this session will be based on GNM, ANM, and ensemble analysis. Ensemble analysis part will be given by Bentley. And I'll try to be my best to cover all GNM and ANM. Okay. Now, I assume that you all have the GNM tutorial downloaded from one of the sources, either from the Google Doc or from the workshop website. Okay. So some parts are just the repetition of the first session, so that's why I'm not going through them. Okay, but I'll just go through the GNM part. So what we are going to do first, of course, we are importing all the packages. It will take time based on the computational power of your machine. Then, of course, now in this tutorial we were working with adenine kinase and its PDBs for ATE. Okay, and either if there is no problem, you're supposed to download it from Protein Data Bank. If you have a problem, you can obtain it from Slack channel. So I downloaded it, or let's say since I downloaded before, so it's already in my working directory, and I'm just like using it there. Okay. So as you remember, this is how you can show structure in ProDy, and then it says there are two chains and there are some water molecules. But as Yvette explained to you, and also Pamela talked about a lot about the coarse-grained models or elastic network models, we are using C alphas. And then this structure for AT is actually a monomer, even if it has two chains. Functionally, it's a monomer. So that's why it's okay just working with one of the chains. And what we're going to do, we're using only the carbon alphas. So that's why I'm using this selection, carbon alphas and chain A. And let's look at how many atoms in this structure. We have 214 atoms in this structure. And now if I just use C alphas for short protein, then I will just end up with this line representation based on C alphas. How about computing GNM normal modes? Since if you know the kickoff matrix, as you had explained, you have everything, right? From the statistical mechanics, we can evaluate the mean square fluctuations or expectation values of 2-point functions. If you would like to go more into detail, you can use this link. It will automatically transfer you to the GNM tutorial page of ProDy. Okay, as I explained before, most everything in ProDy is an object. It's an object-oriented language. And in order to start doing some calculation with GNM, we have to first initialize this GNM object. How we can do it? You can just type GNM, and if you would like to assign a name, then you can just put it here. So this is the title of this object. And then what I'm going to do, I'm hit Shift-Enter. Now I have a GNM object, but it's totally empty, okay? What I need to do, first I need to build the kickoff matrix, right? Since GNM model based on kickoff matrix. And how I can do it, there's just like one function. It's called build kickoff, and it needs coordinates or the atom groups. Okay, either you can build it with the atom group, or you can build it like get coords, and still it works. Okay, now I built the kickoff matrix, but of course there are couples of parameters of this function again, and how we can basically reach out those parameters. You can just Shift Tab, and it says first of all, you have to provide the coordinates. And then there's one parameter here. It's important, it's the cutoff value. As Yvette explained, whenever you would like to put a string between beads, now beads representing what represent carbon alphas, you can put it in terms of a cutoff, okay? You can say if there are two beads, let's look at here. Let's say, for example, here you see, there is a string between these two carbon alphas, but there is none here. So, which means that whenever you create a network for a coarse-grained representation of a protein, you can use this cutoff value, which says that if these two carbon alphas are far away from each other, larger than this spatial cutoff, then do not connect those two carbon alphas. So what is the default value? The default value in ProDy is 10 angstrom. And gamma is the spin constant here, and it is just 1 for all of them. If you don't want to change anything, then you can just, as I said, run it. And then it says it's in just like 0.2 seconds, it build up the Kirchhoff matrix. Now we have the Kirchhoff matrix, but how we can get this Kirchhoff matrix? As like the other functions, we have a getter for this Kirchhoff matrix, and it's get Kirchhoff. When you hit it, it gives you all the Kirchhoff matrix, okay? And as Yvette explained, there is just like, since it's a Kirchhoff matrix, what we know that the summation of each row or the sum of each column needs to give what? 0. This is the definition of a Kirchhoff matrix, actually. And if we use this function, numpy function, we can obtain it. And you see all the values are 0. So it's truly a Kirchhoff matrix. But how about the diagonals? The diagonals, as I explained, are just the degrees of those beads. So which means that, let's say this first residue has how many connections? 17 connections, so which means that 17 beads basically connected to this node. And these are not only, but the diagonals of this Kirchhoff matrix, so you can obtain them. So if you are interested in, or somehow your code needs the degree of each node, then you can just use GNM.getKirchhoff, and then you can take the diagonal. So diag is basically a numpy function. It basically gets all the elements on the diagonal. But of course, the story does not end here, since now you have the Kirchhoff matrix, but you have to obtain the normal modes corresponding to this Kirchhoff matrix. And obtaining normal modes is actually diagonalizing this matrix, right? It's a symmetric matrix, therefore it has either 0 or positive eigenvalues. And how we can do it, how we can diagonalize or evaluate the normal modes, we can use cut modes function in ProDy. It has a couple of parameters. Let's look at those parameters. One of which is, it says the number of modes. So the default value is 20, which means that if you don't change this parameter, it evaluates only the first 20 modes. And it says zeros is false, and true-bow is true. True-bow means it will do the computation in a parallel ways. Zeros means that, for example, this is a GNM model, and it is, as it is explained during the morning session, it contains what? Just 1 zeros, and it has 2 interpretations. One of which is, since this is a one-dimensional model, it has just only one translation in symmetry. That's why one of the eigenvalues is 0, and it does not correspond to a vibrational motion, but it just corresponds to a translational motion. In graph theory perspective, if a graph, since this is a graph, right, it's a network and it's a graph, if a graph has only 1 0, which means that this graph does not have any disconnected piece. Okay, there are 2 actual explanation or interpretation of 0 eigenvalues of a Kirchhoff matrix. So let's, how about how we can change the modes, mode parameter, so we can evaluate different modes. It's easy. What you can do, if you would like to obtain all the modes except the 0, 0, then you can just say none. So it would evaluate all the modes. Since how many residues we have in the structure? 214, one of which basically corresponds to 0, 1. So if I just set number of modes to none, as you see here, it evaluates 213. If I set 10, of course, it will evaluate 10 or 20. This is the default value. It evaluates 20 modes. If I choose the zeros parameters as true, then it also evaluates this 0 eigenvalue. So you end up with a set of eigenvalues which contains the 0 eigenvalue as well. And then let's say we evaluate everything and 0 mode is also there. Then we can obtain those eigenvalues after diagonalization or after calculation of the modes. How we can do it? We can just use this get eigenvalue eigenvalues function. So get eigenvalues gives you all the eigenvalues after this calculation. And if you would like to just see those values with 3 significant figures, you can use round function, which is nothing but an NumPy function. It acts on arrays. Okay? And then, as you see, we obtain all the eigenvalues here. It's very easy. And how about the normal modes or eigenvectors of this diagonalization process? It's easy. You can say get eigenvectors, and it gives you eigenvectors. And each column here corresponds to those eigenvalues. Okay, so you can think that, for example, this is the first eigenvalue or 0th eigenvalue, since indices, as you remember, starts from 0. Then the first column corresponds to that one. Since this is a translation symmetry, what you expect all the values constant, right? Since it basically translates those nodes on graph with this translation or with this value. How about the variances? What is the variance? Variance is the inverse of the eigenvalues, as explained in the morning session. But since now we evaluate the whole modes, including the 0 eigenvalue, I can obtain by basically slice everything after the 0 point. Okay, and then I can easily get those variances. Now, how about plotting? What we know, whenever you have an elastic network model, one of the important things is the contact map. GNM based on contact topology. Or you would like to obtain what? You would like to obtain mean square fluctuations, or you would like to see the mode shapes and also the hinge residues and how we can do it. This is the part for plotting. Let's go back and use the first 2 elements, okay? And which means it does not include the 0 eigenvalue. So we can just use the default values. Now we overwrite the previous calculations, and now we have just 2 elements. As you remember, how we can obtain the contact map, we can either put the structure itself, but since we obtain the GNM map, GNM object, we can also give GNM here. And then here it says, please use this grays as the color map. In Matplotlib, you can provide different color maps in order to color your figure. As you remember, in the first session, whenever I put here the atom group, what it did first, it built the kickoff matrix. But now we already built it, so that's why it just used it. It does not calculate the kickoff matrix here. And as you see, we just like in less than a second, we obtain the contact map. How about the modes? Okay, how about the modes? Since, as Burak explained, those normal modes basically define how all the beads or residues, amino acid residues, moves collectively or like in a concerted way, right? And each value in this eigenvector space will define how much they move. And in order to show or see the profile of the mode, let's say the first mode, what you can do, you can select that mode. As you remember, it's a C-based language. The first index starts from 0. And GNM object implemented in a way that if you provide the index, it automatically selects the modes from that object. So here, what I'm doing, I'm selecting the first mode whose index is 0 and tell ProDy, show me this mode.
Burak, may I interrupt you for a second?
Sure.
There are a couple of questions in the chat.
Okay, I'm looking at.
Oh, okay.
Okay. Yes, some of the functions in ProDy are parallelized. It uses multi-processing library, basically using pool objects. If you are familiar with parallelization schemes in Python. And the other question from Johan, do these functions use NumPy or do they use C to diagonalize a Kirchhoff matrix? It specifically uses SciPy, even not NumPy, since in SciPy you can provide more parameters and flags to evaluate the eigenvalues and eigenvectors. And as you know, SciPy written in C and Fortran. Are there any questions for the technical details? Okay. So let's look at some of the points around 0. Let's think in the following way. So those values are what? The translation, right? In a way that, let's say, you have a normal mode, it allows you to basically vibrate among about all the equilibrium positions, right? What if I have a 0 for a specific residue or pattern, which means that it should be what? A hinge residue, right? For example, I'm just like using my arm here. This is hinge, right? Since the upper and lower part of my arm basically rotates and then moves around this region. So hinge residues are actually important, since sometimes, you know, if you bind something there, you can change the functions of the protein. So in order to show those or see those, what you can do, you can provide this flag. If you say hinge is true, then it automatically put those ones. Of course, some of them are just like close enough, but they're not on exactly 0. But how about their indices, right? We would like to know their indices, which residues. And for example, what you can do the following. The hinge sites evaluation based on the modes. So if you just provide, let's say, if you just use the 0 or the first mode, non-zero mode, then you can just say, okay, evaluate or calculate the hinges based on the first non-zero mode. And then it gives those values. These are basically residue indices. Remember, there is a difference between residue indices and residue numbers. These are internal indices. But if you say, I would like to obtain all those residues not only based on not on the first non-zero mode, but the first non-zero 2 nodes, right? And then you can just say, and then it concatenates the results. So these are the predicted or expected hinge residues based on their values on the profiles, not only for the first non-zero mode here, but also the second non-zero mode. And there are lots of plotting functions. Please just like check this link and look at what kind of functions are implemented. I'm sure you will find highly handy functions you can use in your study. How about covariances and orientations, or like cross-correlation matrices? Since once you have the Kirchhoff matrix, as it is explained during the morning session, the pseudo-inverse of this Kirchhoff matrix gives you the cross-correlations, and cross-correlations basically what the statistical measures of the fluctuations. The diagonal part of the cross-correlation matrix gives you the mean square fluctuations, as we have explained in detail. It's so easy in ProDy. You're just using get covariance, and then it gives you the covariance matrix like this. But there are alternative ways of obtaining covariance or cross correlations. Here, even I'm not explaining ANM yet, make sure that there's a distinction, since GNM effectively is a one-dimensional model. That's why whenever you are asking for the covariance in the cross-correlation matrix, you obtain a matrix with the same dimension, but this is not the case in ANM. So that's why I put this thing here to remind you there are differences between GNM calculations and ANM calculations. As you very well know, ANM is a 3N model, but GNM is a one-dimensional model. And the reason is that GNM is an isotropic model. That's why we have 3 exact copies for X, Y, and Z coordinates. Okay, but in ANM, this is not the case. So whenever you obtain if you would like to obtain the cross correlations, and if you set the norm false, you obtain something like C2. And then since I said that do not normalize the matrix, C2 is also equal to covariance matrix. But this is not the case for ANM. And if you would like to obtain the cross correlations, and if I don't set norm to anything, the default value gives you what gives you cross correlation, which is not equal to covariance matrix. This is like a regression here to let you know there are differences in implementations. Okay, and while you are using it, make sure that you know the distinctions. And as you see, the C3 is cross correlation. That's why on diagonal everything is known. But of course you obtain this, and then you can use matplotlib, imshow or matchshow functions to visualize it. But you don't need to do this since we implemented for you the visualization of the cross correlation as a function, and you can just use this function, and everything comes with the color bar and also the title. And then as you see, now we have the cross correlations, and it basically changes between -1 and 1s that explains. Okay. So what does that mean? If they are positive and close to 1, they are basically their motions are correlated in the same direction. But if they are anti-correlated, they basically moves right against each other. It's good. Now we have the cross correlation matrix and its visualization. And how about mean square fluctuation? As you remember, there are two types of mean square fluctuations. One is encoded in the PDB file. These are temperature factors, it's called B factor or the bipolar factor, and they're experimental values. But our theory also allows us to compute those values, right? And we would like to see how much basically we are successful while evaluating those values, or we can assess our models. Let's say you have a new idea, you would like to extend those elastic network models. What you can do, how you can assess your model, you can compare it with B factors, experimental B factors. But before you do that, you have to evaluate them. How we can evaluate? There are two ways. Either you can use a calculation function for square fluctuations, or you can use show square fluctuations. It evaluates for a year, it plots it. And now, as you see, we evaluate it. But there is one important thing. Before this one, we use default values. And last step, evaluate in order to calculate the modes. And the default value, if you remember, is 20. So if I just use GNM here, it gives me the mean square fluctuation profile for what? Based on 20 modes. Okay, so these are basically this profile based on 20 modes only. But you can say, okay, I'm basically much more interested in the first couple of modes, and still I would like to evaluate square fluctuations. Then what you can do, you can slice GNM. Whenever you slice GNM for the first non-zero mode, ProDy knows that whatever function you would like to run on this GNM object, it just uses those ones, okay? And then now you see the profile changed. Since this time, mean square fluctuations evaluated by using only the first non-zero two modes. And you can also do some like polishing up type of things. We can add grids. This is matplotlib function. You can add grids, and you can also change all the look of this figure just by customizing the parameters of the matplotlib library. So let's say we have this model, or we changed the model, we modified the model, and you would like to compare it with the mean square fluctuations. How we can do it? Whenever you would like to compare it with the experimental B factors, it's better to evaluate all the modes, okay? Now I'm evaluating all the modes. but of course, except 0 mode, since I'm not using it. Okay, now I overwritten all the modes. Now I have 213 modes. And I don't have the equation here, but B factors, how we can relate them. B factor is equal to 8 pi squared over 3 times computational mean square fluctuations, right? So now I have B factors, how I can obtain it, since this is the C alphas, this is a selection, it contains on the C alphas, and then I get the betas for those selections. And then I'm using calc square fluctuations function, which evaluates the square fluctuations based on this elastic network model, which is a GNM. And then in order to see they overlap or not their profile, I'm just using a very straightforward scaling and multiplying both sides by the mean value of the computational and experimental B factors. And then I'm a bit like customizing the figure. I'm giving the size of the figure in inch, and then I'm changing DPI, the resolution of the figure, and then change the colors of those lines, and just using this time the matplot plot function. And also I'm adding labels and say, put grids, put those legends, and try to tighten the plots with respect to the edges. And then if you do this thing, bam, you have results. So what the green one is the computational B factors, and the orange is the experimental one. And now, as you see, it corresponds or it overlaps quite okay. So even if it is the coarse-grained model, and then how much like it takes, we're just like typing a couple of things, initializing GNM, giving the coordinates, and calculating the modes, and then now we can compare it. That's why elastic network models are so handy. They are coarse-grained, and whenever you would like to obtain some information with global motions and compare your results with experimental values, then it's so powerful. And one of the questions, how we can obtain this experimental coupling constant. I'm doing this thing here. Since I know the rescaling factors this time, and I know the equation B factors, B is equal to 8 pi squared over 3 times mean square fluctuations. I'm using this rescaling factor with this 8 pi squared. Why 8 pi squared? Since the model is actually a three-dimensional model, right? We are comparing everything with experiments. Experiments happens in three-dimensional space. But what we know, in GNM, on each direction, X, Y, and Z, we have exact copies. So that's why this part, the mean square fluctuation comes at 3 times one of the mean square fluctuations along one axis. So that's why we multiply it by 3. So we don't have like a denominator 3 here. And then when I just do a bit like algebra, and then I obtain the gamma or like K, this spin constant. This is, sorry, and this is basically your experimental spin constant. And if you do the same thing with dynamics, if you don't want to write any code, dynamics evaluates those rescaling factors and the experimental, effective experimental spin constant for you. And if you do this thing using 10 angstrom as your spatial cutoff, then you obtain the same values. And you can also color your protein with those modes, since those modes allows you how different parts of the protein moves relative to each other. If you would like to use the first non-zero mode, then you can provide it to the parameter mode in short protein. We are using the C alphas and then providing this mode as a parameter, and then it visualizes or it colors the structure with the values. So which means that that part and the red part and the blue part basically moves against each other. What you can do, of course, you can write those values on the B factor column. It's a common practice whenever you have some numerical value of the residues or atoms, and if you would like to see them on the structure itself, the common practice is writing those values onto the temperature factor or B factor column. And it's so easy to do this thing in ProDy. What you're doing, let's say I would like to color code my structure in VMD with the mean square fluctuations based on the first 10 non-zero modes. Then you can evaluate those values, like here, calc square functions. You can slice the GNM for the first non-zero 10 modes. And then you say, okay, write a PDB with this name, and then use the C alphas only, and write those mean square fluctuations on the beta. There was a question just before the end of the first session, and the question was the person, I don't remember his or her name, so sorry about it, but he or she could not show the secondary structure. Yes, I will show you how you can obtain a full-fledged cartoon representation in ANM tutorial. Here, as you see, this is the C alpha, so which means that we don't have any atom in the structure, right? Only C alphas. And I say this, where now I have it, for example, this is my folder view, it's there, okay, it's there. How we can run VMD, there are a couple of ways. If VMD is in your path variables, you can run VMD from Jupyter Notebook, just using this exclamation mark. It tells Jupyter Notebook, this command is not a Python command, but it's an operating system command. Generally, this works with Unix-based systems or Linux-based systems. Sometimes it does not work, even the VMD is in your path in Windows. So if you are using Linux and if you would like to test it on Windows, then you can, what you can do, you can uncomment it and you can run it, okay? And if you would like to run VMD with the PDB, automatically you can also say this thing. But I'm gonna do it in a standard way, just running VMD externally and then parsing the structure. Okay, so this is my VMD. I think you all have VMD at somewhere on your machine. I'm running VMD now. Okay, so it comes. So I need to drag this thing to this screen, and I have the VMD. Okay, what I'm going to do, I will load this structure, and I will come to File, and then New Molecule. After choosing New Molecule, I will go to Browse and go to the directory in which this result is saved. Of course, it is different in your system. So in GNM, and that's the file. So I open it up. After the browsing, it just says load, and it comes there, and you see there are just dots. Okay, why? Since we don't have any heavy atoms. But how we can show it? There are a couple of ways. First, let me change the perspective to orthographic. And then I'll go here, representation, okay, from the VMD menu, just go to graphics and representation. And then it opens up a new window. What you can say, drawing methods. Since I don't have any heavy atoms except C alphas, I can just use tube. Now, as you see, we have a tube representation. In the next tutorial, I will show you how you can make it cartoon. Okay, so now we have this tube representation, but what our original intent is color code this protein or this visualization with betas, right? How we can do it? There's a drop-down menu here. It's called coloring methods. Just like click it and choose beta. And now we color code it. Default color scale is from red to blue, but we can change it. Since normally we are so accustomed or let's say predisposed to see red for the most mobile part. So how we can do it? Just comes to graphics again, and then choose colors. As you see, this is also some kind of a VMD tutorial now. And then what you can do, you can go to color scale. So if you are using the latest stable release, you can just choose the method from here, blue, white, and red. And now as you see, so this is the lib domain, this is the core domain, and this is the MP domain, and these parts move a lot. If you install alpha release, like here, then you can also change it to this one, okay? And it will be a bit easier to see all the more fluctuating parts or less fluctuating parts, okay? Even what you can do, you can change the color of the background, choose color definitions and display and the background, and the 8 is the white, and you can check it, and then now you have this one, okay? It's not good for eyes, but that's the way. And then you can even change the material to show this thing. You can make it, for example, chalky, and it becomes more crispy and fancier. For the production purposes or publication purposes, it's better to use A or chalky, okay? Now you can change the resolution, you can increase the resolution. And if you don't want to see any shaded areas, you can come here, display, and then display settings, and then you end up with, okay, I'll try to, you can end up with display settings, and you can change the Q mode to linear. And then now there's no ghost or shading effects. Okay, that's good. That's good. Let's continue.
Burak, before
Yeah.
you continue, I see a couple of more questions in the
Sure.
chat. Do you wanna?
Okay, I'm looking at them. Okay, good question. Can you explain a bit more what hinges are? I will come to that point if you allow me in the next tutorial, okay? In the ANM tutorial. Since we have a movie, okay, we will learn how to see the motions, global motions in VMD. Then I will try to give more information. If I forget it, just remind me. Is Dynamics actually working right now? No, Dynamics is not working. I'm doing everything in VMD, but you can also do this thing in Dynamics. If you are asking if you tried Dynamics, that if the question is the server is working or not, Dynamics, I think it is working. And let me check. That's working. It's working. Okay. So the next thing is flexible loops or terminals. So let's say you have a structure. Here the structure is this one. Okay. And then if there is a dangling ends or like highly flexible like loop ends, then what we're going to do, since it can overshadow our results, right? So for this one, I'm using this PDB, okay, 1AAR, since that structure has this flexible loops in it. What I'm doing still, I don't want to download the compressed version, and I'll just use the first chain and CFS. And there's another function. If you don't want to first initialize a GNM object and then build the kickoff metrics and afterwards evaluating the modes, we can just do this thing in just one sentence or line of code. We can say calc GNM. This is like a shortcut version of everything. You can define the cutoff and you can give the atom group, and then it basically initialize the GNM, build the kickoff, and diagonalize your kickoff metrics. Let's do it. And as you see now, we have a region, since before we don't have such a part, right, in square fluctuations. But here we have that thing. This is the mode version, but we can also evaluate the mean square fluctuation. It says that n basically moves a lot, right? And if I color the protein with this one, you see there's some part of the protein is highly, let's say, like disconnected. It's not disconnected, but let's loose ends. And basically it can oscillate a lot. What we can do, we can do the following thing. If you remember the first session, we can use mathematical operations to slice, right? Slice any part of the PDB file. And I'm doing it. What I'm saying here, please evaluate or calculate GNM modes just using the residues whose residue numbers is less than 71. Okay, I'm checking the chat again. It says it does not work. Let me check this one is working or not. Maybe there's a problem. But let's say a 10 and give it, and then, okay. It turns out that there's a problem with the server. Okay. There wasn't a problem early in the morning, but maybe something happens. We will check it. So now I'm using a slice. It contains all the residues up to 71, right? And then I'm evaluating everything. This time, as you see, since we don't have that part, we can see much more details of all the parts of the modes. And then whenever I color the protein with this one, I obtain this structure. But why it is important? So as you see, what we explained early in the morning, the first couple of modes are highly collective and global modes, right? So collective means those modes allow the structure move in one direction among one of the normal modes together, right? And there's a nice function in ProDy. It evaluates the collectivity. It's a measure based on entropy, and it evaluates the collectivity of specific modes, okay? And you just need to give the modes, okay, to evaluate. For example, this one is the non-fixed one. It contains that dangling end, a flexible part of the loop. So whenever I evaluate this one, it says the collectivity of this mode is high-low, right? High-low, since that probably the first mode is now responsible the high fluctuation of this end. But when we fix the structure in terms of just parsing the part of the protein whose residue number is less than 71, then it becomes, as you see, the collectivity becomes much more higher. So if you would like to see the collectivity of different modes, let's say the first 10 modes between the structure which contains this highly flexible or loose ends or dangling ends with the fixed one, we obtain this plot. As you see, whenever you fix, then you can see the first mode becomes much more collective. So this is basically the very crash course on the GNM, and we will continue with ANM. But let me please give me just like a couple of minutes to just rest and refresh myself, and then I'll come back and start ANM. Okay. And the answer, can I compare collectivity between two similar structures to different proteins? You can evaluate collectivity for every structures. And then the another one is, what if you want to use selections of alternated segments? And what do you mean by alternated segments? If you be more specific, I can answer the question.
Okay, so can you hear me? Hello?
Yes, yes, we can hear you. Kwani?
So you selected a chain earlier. So I was wondering, what if you wanted to like select a particular segment that kind of repeats itself? And you wanted to like do the mean square fluctuation of that of those segments.
So if you would like to use a portion of the structure itself, then
Yeah,
you can,
and let's say it repeats itself like, along the backbone. What would you do if you were trying to find like the mean square fluctuation of those particular segments?
mean square fluctuations based on your atom group. So you cannot extract that part. So since kickoff matrix based on the contact topology of your structure, and the code does not know it's a structure or a portion of the structure, whatever the atom group you give, it evaluates for those ones, right? Since you're defining a cutoff. So if you just use some part of it, then you need to create another network for that part only.
Okay, thank you.
Okay. But of course, for example, here, when you look at the mean square fluctuations, let's go back here, right? So let's say you're much more interested in this part, right? That part, for example. So as long as, like, if you don't want to use isolated segment here, those residues also connected to those ones, right? The other ones, based on the cutoff. So that's why you cannot just take this thing out and trying to get some mean square fluctuations for specifically that portion. Everything based on your starting network, how you build up this network. But you can just read, of course, the mean square fluctuations of that portion, but still that portion will be a part of the bigger network.
Okay, thank you.
You're welcome. Okay, I'll just like stop.
Burak?
Yeah.
Yeah, just a quick question that's kind of lagged a bit. I was going to ask earlier, even before when you were doing something like generating a PDB structure and you had C alphas only, is there an option to not choose C alphas and produce all currently available atoms colored by residue type for mobility?
Yes, exactly. You can give that, for example, in select command, you can say not C alphas, then it will just like select the other atoms, not C alphas.
So you can actually write down not C alphas, that's the word.
Yeah, yeah. And then let me go, for example, here, go to CSP.eu, and then go to tutorials, and then tutorial here, and then atom selection. Okay, these are all the things we can do. It's very in detail. Okay. And then even if you would like to go more detailed selection algebra, then you can choose atom selections here, and then you can obtain more options how you can do it.
Very cool, thank you.
Welcome, welcome. Okay, I'll be back in minutes. Okay, now I'm back. Everybody's here?
Oh, yeah, I just announced that you will be back in 10 minutes.
No, no, no. It's just like 1 minute.
Sorry. Yeah. You can leave. It's not too late.
Yeah, let's continue. Okay. If I'm not tired, nobody's tired. That's the deal, okay?
Okay, cool.
Okay, this time we also need another PDB if we have still downloading if you have still problem with downloading them. So I'll just share the other PDB. Okay. Now it is time for one AT and ANM. Okay. Okay, one question, and I need like sincere answer. Are you having fun?
Yes, it was great.
Okay.
It's awesome.
Okay. So now all of us know we first need to import all the packages required, and I did it. So now this is ANM tutorial. Here, what we can do, for example, Yvette and Pemra told you the deformation vectors. If you have, for example, apo and bound structure, you can find a vector which allows you to go from one structure to another by using this vector, right? You can create some trajectories, and we will learn it. And also we will learn how to visualize normal modes in VMD this time. And with all the secondary structures, we can have very nice, beautiful let's say, visualizations. So first, what I'm doing, I'm parsing for a key, which is the apo form of this adenoid kinase. I put AA, it stands for all atoms. And then now I'm selecting just carbon alphas, as I did in GNM. Now I have them. So it was almost 2,500 atoms, and now I have just like 214 atoms. And I'm doing the same thing for the bound form, okay, or complex form, and choosing the chain A and C alphas again. This time, I would like to initialize an anisotropic network model. It's again an object, so I can initialize it. And I'm giving this name OpenAKey, AKey. Now I initialized it. This time, as you know, we are not building Kirchhoff matrix, but SU matrix. It's a 3n by 3n matrix. And building it. Now, in this object, we have the title, we have the atom groups to generate the Hessian model, Hessian matrix, and now we have the Hessian. Of course, what I did, without telling you, I used what? The default parameters. Let's look at what kind of a parameters this time. As you see, similar. We need to provide the coordinates or the atom groups and also use the cutoff values. As you remember, in GNM case, the default cutoff or spatial distance cutoff is 10 angstrom. This time, the default value is 15 angstrom. Okay, I don't change anything, and then I build it. And then what I'm going to do, I will diagonalize it. Actually, ProDy will do it for me. And I said, okay, I'm not changing the default values again, so the default modes are 20. Now I have 20 modes, okay, after diagonalizing it. So I have eigenvalues and eigenvectors, okay? But at the same time, make sure that you know the differences in terms of those zeros. ANM is a three-dimensional model. It's an anisotropic model. Therefore, this time we have actually six zero eigenvalues, and they correspond. The three of them correspond to translation among X, Y, and Z axes. And three are rotations around its symmetry axis of the molecule, or in the lab frame around X, Y, Z again. That's why in ANM we have 6 zeros. Okay. Let's look at the modes this time. since it's a three-dimensional model, this time, whenever you would like to see the modes, you obtain those X, Y, and Z components of the modes, okay? And the same thing as, for example, if you would like to evaluate the square fluctuations based on just one of the modes or a couple of the modes, then still this show square fluctuation methods, it's like a class member, so that's why it can act all of the objects, even though objects are different. Here, this is the case for ANM. It acts on it and it evaluates the square fluctuations based on the first non-zero modes, okay? But if you would like to obtain this thing for all the modes computed based on the parameter you provide to the ANM object, then it evaluates this one. So here, the default value is 20 modes. That's why if I don't slice anything, it regenerates the square fluctuation profile for the 20 modes, okay? And then if you would like to evaluate the cross correlations, then just use this function, give the whatever the mode you would like to use, and then bam, it evaluates for you. And then later for your publication purposes, you can also customize this clause. And if you would like to use all the modes in the cross correlations, then you don't need to slice anything, as I said, and then it evaluates now the cross correlations based on 20 modes. But how about visualization those modes, okay? In VMD, we have this normal mode wizard, and it basically opens NMD.NMD files, and we can generate those files in ProDy easily, okay? So first, okay, let me do the extension first. In GNM, we did everything based on carbon alphas, and then we basically wrote the mean square fluctuations on the B factor column. And then when we open this file, the PDB file at that time, open in VMD, we obtain just like we saw only the points representing carbon alphas. Now I would like to extend those modes to the whole heavy atoms or all the atoms in the protein. And there is a function for it. It's called extended model function, okay? Extend model function. What it does, it gets your modes and it extends to one atom group to another. Here, since we evaluated modes based on carbon alphas, after giving those modes, we first specify the atom group on which these ANM modes evaluate. And then we give the second atom group to which we extend those modes, okay? And then when you do this thing, it returns two objects, one of which is extended model. In this case, is the ANM model. The second one is this atom groups, okay? And then we can use these two objects to generate an NAMD wizard file to open in VMD and visualize those modes. And then the command is expected, write NAMD. First, you provide the title, and then you provide the atom group, a model, sorry, and then you provide the atom. Okay, and now I'm doing it. Okay, it's there. So let's open it. This is the second time we are using VMD. I'm going back, I'm running it. This time we do more customizations in VMD. And I'm sure on the third day, when they start using VMD, you already know a couple of things about VMD. And it will be easier for you to learn the details of VMD. Okay, so this time what we're doing, this time, first, since we write this function as an NAMD file, and it's a normal mode wizard file, we're basically clicking extensions, and then analysis, and you're going to normal mode wizard. Then it opens up this little window, and it wants us what a NAMD file. I'm clicking it, and then it opens up this one, So I have to go to the directory in which this NAMD file is saved. It's here in my machine. And open it. Wow, counts this one. There are lots of vectors in it. Okay. So this time what I'm going to do, I'm going to do the same thing again. I don't want to see in perspective modes like orthographic, and then display settings. I would like to change the Q modes from exponential to linear, and then it's good. So these are the things. And what are the options for this? As you see, this is the active mode. You can change the mode. You can change the color of the mode. But let's first make the play. Okay, I would like to see the motion first. Now it goes. First, I would like to hide the modes and the original. As you see now, it takes place or moves. But I would like to change, since now I have all the atoms in my file, I can change the representation in a way that I can show all of them. I'm going to use new cartoon. Now, bam, I have this one. Okay. And then I would like to change, and automatically, since it's a NAMD file, it realized that it needs to color everything with the B factor. But still, I would like to change the scale, and let me change the scale to this time again rainbow. If you don't have this one, you can just use blue to white to red, and then oops. I have this one, as you see, it goes like this. And then I will change it to a nicer one. Wow. So what we know for those normal modes, it's basically moves or oscillates around what? Around an equilibrium position. If you look at this one, we have 51 frames. So if you set this thing to 26 and then show the vectors, they start from the structure, but there are too many vectors. Since we extend everything to all atoms, what I'm going to do, I'm changing the selection from here, say name CA, and then redraw it. You see now what we have all the vectors on the carbon alphas. So you see, right, the first mode basically moves the lid domain and the MP domain against each other. Let's see it. Whenever I make it like this, you see. So the question about hinge sites, right? If you look at this one, for example, these places looks like a hinge, right? Since it moves like this. So these are probably the hinge sites we found before. And if you don't want to see the vectors, then you can just hide the vectors like this. Let's look at the second one, what it does. Oops, sorry. I'd like to see what the second one does. Now, it shows like this. Of course, I have to generate the movie for this mode again. Now I have it. Whenever you generate another movie or structure for this mode, you have to change the representation and choose the correct representation again. So now we have this one. What it does, as you see from the top, if Y is out of the page or from the screen, it basically rotates around Y, right? So now we can see all those global modes. In that way, since those global modes also facilitates the function of the protein, you can also infer important parts of the protein. Okay. And so, as you see. And if you would like to change the color again, you can go and you can change the background and you can make it white see, let me close, hide the modes. And you can analyze the global modes or the motions of your protein, just changing the modes like this. Okay, it's very good. So let me stop and continue. So what is the next thing? I show you how you can superpose the structures. I'm not go over this one, but if you would like to, let's say now you have 1 ATE and 4 ATE, you would like to see them on top of each other. This is homework. What you can do, you can superpose the structures. The RMSD difference between closed and open structures is 75 angstrom. You can superpose them, or in other words, you are aligning them. And then after aligning them, you see the RMSD difference. Now it's 7 angstrom. You can write not only the carbon alpha based open structure, but also carbon alpha based aligned structure. And please try to open these two structures and also the non-aligned one, and see where they basically located in 3-dimensional space. And you can just play with this. But another important thing is deformation analysis and the comparison with ANM nodes. What does that mean? As Yvette explained and also Pema elaborated on it, if you know two different structures, for example, bound and apo, or complex or apo structures of the result structures of the same protein, then you can evaluate the deformation vector, which allows to go from one structure to another one. At least it can show the direction how the protein basically changes or deforms along these functional modes. In order to do that, of course, you first align the structures. That's why there's this section here, alignment section. After aligning the structure, you can provide these two structures and ask ProDy to calculate the deformation vector, which basically takes one structure to another. Okay? And then you can see what is the dominant one for those deformation vectors. It's so easy. There are two visualization functions. At the back end, they are calling other functions like their calculation versions, let's say. The first one is the overlap. Since we know, as it is explained early in the morning, those ANM modes and deformation vectors from one structure to another one, for example, the apo complex, they basically overlap each other, right? Since the protein using those accessible modes of motion to change its conformation. So here what we're doing, we are basically evaluating the overlap of these two motions in order to see that which ANM mode should be used to generate some trajectories to understand how this molecule changes its conformation. And then it turns out that the first mode is the highly dominant. Again, don't forget, make sure that indices starts from 0. So which means that if we use the first non-zero mode, we can infer or visualize how this molecule moves, right, from one state to another. Now, how I can do this thing? I can do this thing either based on the carbon alpha. I can either use the models, elastomorphic model based on carbon alphas, or I can use its extended version. For the carbon alphas, you need to use traverse mode. It generates trajectories. Okay, it generates trajectories. And how it generates, you have to provide the mode you would like to use it, atom group, and the RMSD of each generated frames. Okay, and then since it's a frame, if you are familiar with molecular dynamic simulations, you have to set the atom groups always to the trajectories. And what I am doing is I'm generating those trajectories and then setting up the atom information or atom group information. And then if I evaluate the RMSD difference between my target and the last frame of the trajectory, which I have created just before this cell, it becomes 5.6. So as you remember, it was the aromaticity difference between two structures, two states, let's say, here. It's 7 angstrom. Now I just like get close to actually to my trajectory, at least come close to 5.6 angstrom to the target point. But of course, in order to visualize this, what I'm going to do for all the cartoon representation of all this secondary information, I'm also using this expanded model to create the trajectory. Okay, this time I'm using atoms all and the all atom ANM model, yeah, an isotropic network model, just using the first non-zero mode since I know it's the dominant one. Okay, and then I'm setting this time not to carbon alpha atom group but to all atom. And then, okay, we generated this. And then what I'm going to do, I will write them as a PDB. And what it does, since I have frames, it puts those frames as a different models, like the NMR structures, right? In NMR structures, you have different models in NMR files. So let me come back here. I'm here now. What I'm going to do, I will just delete all of them. I don't need them. So this time it's a PDB file, so I can open it here, new molecule. And then browse. And then this time model, AA, PDB, and log. And I have this one. Of course, I'm going to change the representation to new cartoon. Now I have the structure. Let's move it since it contains those frames. You see? So that was a dominant one which overlaps well with the deformation vector. So we generated trajectories using this ANM mode, and now we can move it. Of course, some of you maybe realize that there are some places like broken, since we deformed the structure, but we didn't relax it, okay? In order to make those parts connected, you have to do a minimization on the structure. Then it becomes connected and relaxed, and you can still use it. But as Pamela told you, we have, for this one, we have highly efficient techniques, one of which is CoMD, and another one is Class DNMD. And you can also reach out their tutorials. They are highly self-contained and explanatory, and you can sample those confirmation space. And then at the end of the day, you can use those frames to see how the different states of the same structure can be obtained. So this is all I can show you. I hope you enjoyed it. I'm so sorry for the problems for installations you experienced, at least some of you, but at least now you know how to use it. The Ensemble one, Bentley will explain after maybe 10 minutes, I don't know, but these are the fundamentals, since in Ensemble analysis, or for example, tomorrow, SIND or ESSA or membrane ANM, we use all those basics. If you have enough energy, make sure that tonight, just like go over those tutorials, try to play with them, try to open them in VMD, get a bit more familiarity, and tomorrow it will be much more easier for you to understand the other modules and the techniques we have.
Just to make sure, we're looking at the Ensemble analysis Jupyter notebook file, and you should also download this data file they have here and place it in the same directory that you're running your Jupyter notebook from. The Ensemble analysis that we're going to be doing today is mainly going to be using to compare our experimental data that we're going to generate using PCA and data predicted from our ANM results based on what Burak just showed us. So to start off with, we want to do our imports, ProDy, NumPy, and Matplotlib. And we're going to be using this P38 structure again. So if you run this line, you'll probably just get this file is found in working directory, so you shouldn't have to query the PDB again. So what we're going to be doing is building an ensemble of P38 structures from the PDB. And so what we're going to be doing is using this blast PDB function. So this is going to use the sequence of the P38 structure that we can get using this line. So P38 chain A dot get sequence. So it returns the protein sequence of this structure. And so if we wanted to actually run this blast search, this is the line that you would use. However, it's commented out now because we don't want to just run 40, 50 versions of the same search on their server all at once. And so that's what the data file is. So we can go ahead and open up this data file. So it's a pickle file. So pickle should be just another package that is built into your version of Python. So if we want to do pickle.load and open this blast record 3.pickle file. And then, so this is a ProDy blast PDB record file.
Bentley, I just saw a question in the message. Rika asked, can you please share .ipynb file? I'm not able to locate. And just copy and perfect. You can either put it in the Slack channel or in the chat here, whichever is.
I already shared
Okay.
in Slack.
Okay, I just sent it in the chat also. So, okay. So next, what we're going to want to do is filter out some of these results that we got from searching the PDB. And so what we're going to be doing is basically getting rid of sequences that are too similar. So we don't want to just keep doing basically just different versions of the same structure. So after we do our filtering, we have 253 structures here. And so if we do like Burak showed with this slice, we can get the first 10 PDB IDs that resulted from the blast search. So you can't find the pickle file.
I will share this one as well.
Can you? Okay.
I think there is a problem with the internet connection of the university, maybe. So I will.
Yeah. Seems like the servers, yeah, behaving oddly. Okay, so Burak is going to link to the pickle file. And then, okay, I'll just go to the end of this section and then wait a couple minutes to let people catch up that need to. So basically now what we're going to do is this box is going to just make a new directory to put all of the PDB files in, just so you don't mess everything up in your local directory. So it's going to make this PDB directory, PDBs, and then it's going to set the active directory to that one. So then when we do our parse PDB, we're giving it this list of all of these PDB IDs that we got from the blast results. And so that's going to download all of these structures and put them into this PDBs directory, and then reset that. So if everyone can run that, it'll take probably a couple minutes with everyone doing the retrieval at the same time, depending on your machine and your connection. So we can just wait here for a minute or two while people get caught up. And if you have any other questions at this point, feel free to ask.
I'm going to make comments about the files. Now I checked that the web server returned back. It's up and running. I think there was a momentarily disconnection, but now we can download it from the server as well, the workshop web page of ProDy. And there was a question about the pickle file should be in the same location with the Jupyter Notebook file. The answer is yes, since it tries to this time load this pickle file. Okay.
Yeah. So when you're doing like open file or something, it's just looking in the same directory that you're running the notebook off of. If you needed to have it saved in a different place, you could have it somewhere else and just give it the full path to whatever. If your file is saved somewhere else, but yeah, it's easiest just to have it in the local directory.
Quick question. I'm asking ahead of time while we're waiting for the things to download. Well, if we perform PCAs, can we also perform PCAs from example DCD files and then combine those with X-ray structures to get like a global, the same PC for each of the X-ray structures using the PCs from the MD simulation?
So are you asking if you can perform PCA based on the simulation results?
Yes,
doing like an MD
from
simulation?
a DCD file and also combining the X-ray. So for example, I ran my MD simulation, let's say 1 microsecond, I calculate the 2 principal components, and then I want to project into those principal components the PCAs of the X-ray structures to compare it to what I got from my MD simulation. Can I do that with ProDy?
I have not loaded a DCD. I think you can. Burak, do you know if you can?
Yeah, the answer is the following. If you would like to create a larger ensemble, which contains not only your DCD frames, let's say DCD file, which contains your frames, and you also would like to put the PDB structures, you can do it. But in order to do it, you have to use the same atom group, okay? Since in your frames, you will have hydrogens, missing hydrogens. Since you are doing MD simulations, you have to put those hydrogens back into structure before doing the simulation. In order to combine different structures, atom groups should be the same. Then you can evaluate principal components based on not only the your simulations, the frames, but also the X-ray structures. Then you can project all of them onto the PCs of this ensemble. But if you would like to, for example, project your experimental structure onto the space spent by the PCs based on your DCD files, then you should not put your X-ray structures into that ensemble. Okay, so there are three ways you can do it. One way, you can evaluate, you can generate the ensemble based on experimental structures, evaluate PCA, and then project your frames and also the X-ray structure onto the subspace defined by those PCs. Or you can just create an ensemble based on your frames and then project everything onto the subspace spanned by those PCAs. Or you can put all of them into one ensemble and generate PCs and project everything onto that subspace. Okay?
Yep, thank you.
And the important thing is here, if you have lots of result structure, experimental structures, you can think that it's the ground truth if you have enough structures, of course. But for example, for the case of the ATEM, I think Pemra explained today, the experimental structures are, even if we go down to 50% sequence identity, still you have a couple of structures, almost like 50 maybe. Then whenever, for example, project your MD snapshots onto the space spent by the PCs based on the experimental structures, those experimental structures occupy a very narrow place or region, but your MDs samples a larger space. So it depends on the number of result structures. Okay.
Thank you.
Okay.
So is anyone still trying to download structures? Just wait a minute in the chat, see if anyone is. Okay. Okay. Okay, a couple people are still waiting. I'm going to keep moving on though, because we're getting kind of short on time. You can, you might have seen, but while one thing is running, you can still queue up different selections to run, and they'll just run once they finish going. So, so the next thing we're going to be doing is using this, setting a reference chain. So we're looking at the chain A from the P38 structure, and we're doing just a specific selection here. So looking at just getting C alphas for these specific regions of the structure, and we're going to use that to and we're going to use that for our building on our ensemble. And so what we're going to do is we're going to insert that selection of the chain A into the first position of our PDBs list. And then we're going to run this build PDB ensemble function. And so what that's going to do is it takes in our list of PDBs. This is just the mapping function. We give it a title, P38, and this reference, ref chain, is what we're going to be using to align all of the structures that we downloaded from the PDB to. And so, as you can see, it's mapping each PDB to the reference. Oh man, I usually don't run this on my laptop. It's usually not quite this slow, but yeah, basically what that's doing, it's going through and taking each structure that we downloaded, comparing it to this reference chain, and then mapping it. So finding the parts of the structure that correspond to the reference structure.
While we're waiting, can I ask quickly, is it going to chop those parts and then we're only going to analyze that subsection that has overlap?
So there's a couple different, let's see if this will work. Okay, so there's a couple different options that you can do. I don't know why mine didn't show up. Okay, so is that not in the build PDB function? Okay, sorry, that's a different function I'm thinking of. So I believe what it does is any unmapped sections of the PDBs, it's just by default, it's just going to get rid of or just ignore them. So
I
in
can
one of,
add a couple of things to this answer. If the reference chains has less atoms, then yes, there are a couple of features. Either it uses the structure that chop off the other atoms from the other structures which has more atoms, or it can use an environment methods you will learn tomorrow. If the reference structure has more atoms, then it puts dummy atoms. So in a way that if you would like to create a build PDB ensemble, it's better to find the structure which has the least in order not to have lots of dummy atoms in your other structures which has more atoms. Yes.
Thank you.
Welcome.
okay, yeah. So after it's finished building the ensemble, you can just show the ensemble data structure. So it's a PDB ensemble, the title that we gave it. And then, so we have 278 confirmations, which is the number of structures from the PDB, from the blast search that we got, I guess, +1, from the one that we inserted, and 321 atoms long. So looking at these ensemble dynamics, what we're going to do is starting off doing a PCA analysis. So what this is going to do is we're going to identify the components of this structure that account for the highest amount of variability. So in the different structures that we give it. So this first line is initiating just an empty PCA data structure. Then similar to how we do with the GNM and ANM, we're going to build the covariance based on the ensemble that we give it, and then do calc modes, which, like the other ones, is going to by default just give us the top 20 modes. It just takes a few seconds to run. So then what we can do is iterate over these first 5 PCA modes and show, use this function. So calc frac variance. So this is going to take whatever mode that you give it and calculate how much of the variance in the data structure that particular mode accounts for. So for this P38 ensemble, we see the first 5 modes account for well over 50% of the variance in this structural ensemble. So next we're going to just do an ANM analysis of just our reference chain. So it's similar to what Burak showed us before. Just make an empty ANM model, do build Hessian of our reference chain, and calculate the first 20 modes. And then, so what we can do is compare the collectivity of the modes generated that we observed in the PCA against the ones that we calculated for the ANM. So what this represents is the amount that each mode recruits is kind of a weird word. So it's the amount that each mode affects the overall dynamics of the structure. And then what we can do next is look at the overlap between the modes generated by PCA and ANM. So this print overlap table will just give us a text-based table of the first 3 modes, and then the amount of overlap between each combination of these modes. If we wanted to see that graphically, you can just do show overlap table and give it the number of modes for each one. So what this will do is it plots the absolute value of this overlap. So from 0 to 1 of each combination of modes that you give it. So as you can see, the first mode for both the PCA and the ANM gives us around an 80% overlap. And then, for example, this 4th mode of the PCA maps very well with the 2nd mode of the ANM. So I don't know why that's skipping that. But so this next function is calculate the cumulative overlap. So basically with the first mode of the PCA, so it's looking at this column and then it's going through and adding up the overlap for each of the modes generated by the ANM. So each one of these is an ANM mode, the overlap. And so as you can see, we get almost all of the overlap with this between these 2 methods by the 3rd mode of the ANM. And so if we want to compare these modes directly, what we can do is use this show scaled square fluctuations function. So we're going to give it the first mode of PCA and ANM, which had this, I think this might be a different value because I think I might have saved the wrong one. But if you can just change this to PCA bracket 0 and ANM bracket 0, it will give this plot. So as you can see, there's a very high amount of overlap, which is to be expected. The plots look very similar once they're scaled between the PCA mode 1 and ANM mode 1. If we wanted to look at another combination of modes, this one is, so this is, like I mentioned, the PCA mode 4 and ANM mode 2. You can see that, again, there's a pretty similar correlation, except for around this specific part of the protein, where there's a large difference in the modes generated by ANM and identified by the PCA. So we can also compare the cross correlations of these 2 methods, of the modes generated by the 2 methods, by doing just the show cross core in PCA mode 1, ANM mode 1. Again, these are quite similar as we would expect given the amount of overlap between the 2 modes. And then we can also just write this to both a PDB file or an NMD file in order to visualize either in PyMol or VMD using normal mode wizard like Burak showed us before. So are there any questions, or is anyone getting stuck anywhere with anything?
It looks like everything went fine this time. Thank you, Bentley. It was a great talk. So there is a question for you. Eddie is asking, what is the interpretation of the PCA and ANM table?
Are you talking about the overlap table? So
Yeah. I'm just curious, physically, what does it mean, the fact that you have some, is this just saying that these two bases, these are what the similar bases vectors are, or is there actual more physical meaning to them?
So these, okay, yeah, it's the correlation cosine. So these values are just the similarity between the vectors generated. So that the zeroth, in this case, eigenvector by PCA or by ANM, 0, 1, 2. So basically it just goes through each pair of eigenvectors and calculates the correlation cosine for each one.
So just sorry to, but so I'm trying to understand what that means. So basically, if you had something that was completely diagonal, it would be saying that both bases are essentially equivalent. And so if you have something that's non-diagonal, that means the bases aren't equivalent.
You mean in this plot? So if like the highlights are showing up off the diagonal, is that what you're talking about?
Yeah, exactly. If your high values were, not on the diagonal, is that just saying that, what one basis called vector 1, the other one called vector 3, and there's no real significance? Or is there some significance to the two not being perfectly overlapped?
Oh, okay. So yeah. So the ordering of the modes isn't always going to correlate exactly. There's also the issue of, so our PCA ensemble is generated just from the entire sampling of structures in the available in the PDB, whereas our ANM results are just from one specific one. So if you did an ANM analysis from a different structure, or a different, yeah, I guess a different structure of the same receptor, it's probably going to give you slightly different results just based on the fact that ANM isn't going to perfectly recapture the entire ensemble of possible structures. But
I can give a couple of comments on this, Eddie. So as it is explained early in the morning, it turns out that the global modes, they are highly accessible to the protein, right? And when protein tries to change its conformation, it uses those highly accessible modes. So PCA actually gives you the variation among the different result structures, since how many structures result, for example, here 200, right? And then you're looking at the variation. So let's say if you did this thing for the AKA or adenine kinase, you can maybe see this structure opens up the lead and the core domain, MP domain, and in the bound form, it is like this, right? So how the structure comes from or goes from this state to another one basically uses those highly accessible normal modes. And then that's why, for example, every normal modes are physical. Since why? What you are doing, you are cooling down the structure, right, in order to do the X-ray experiments. And then when you cool down the structure enough, in quotation marks, then you only see the vibrational motion of the structure. And it turns out that structure is using those vibrational modes, the collective ones, or the global ones, or the slowest ones, or the functional ones. We use this like interchangeably. It uses those modes from one state to another. So whenever you basically evaluate the correlation cosine between PCAs, which describes the variation on the ensemble of your structure, whenever those ones basically overlaps more, then it means that structure uses that mode from changing its state from, let's say the, I don't know, the closed one to an apo one to complex one, or let's say it uses those ones to go through the transition, for example. The deformation vector gives this one. In that way, what we see here, the vibrational modes, especially the first couple of them, are so important for the protein itself to sample its conformations. The correct interpretation is this one. So, and for example, if you do this thing via MD simulations, since you cannot sample enough, why? For example, maybe your MD simulation stuck in a minimum, right? And then you cannot sample around more. Then you cannot see those ones in a short MD simulation. Then you have to have a long MD simulation. Even it's not guaranteed that you can sample enough. But using this elastic network models based on vibrational spectrum, you know that some of the modes are highly accessible and allows you to sample the conformational states. And what is the ensemble here? Ensemble is the X-ray result structures. So the current view of, for example, which is very important for the druggability studies, we know that structure itself, protein itself, sample most of the conformations, and the binding does not create new conformations, but binding facilitates makes the molecule choose one of the, for example, complex ones, right? And from the PCA analysis, we see that the variation among the ensemble, of course, the variation can be obtained if you have enough X-ray result structures. You can see how this structure changes, right? And from this ANM part, all the modes are physical, since it's a complex vibrational system. Then you can obtain those modes to match and to see how we can go from one state to another of the molecule. Is it the answer of your question?
Yes, thank you. I appreciate that. Thank
Sure.
you very much.
Welcome. You're welcome.
Hi, may I have one observation?
Sure.
Sure. The point is on the square fluctuation part. Can you go there, please? I have one question. Yes, that's part. Okay. Because in my file it was, instead of 0 on PCA and ANM, it was 1, and now I changed to 0, and now it's the same. Okay, thank you so much.
Yeah, I think when I uploaded it, I had like changed them last year as I was going through and give a different example.
Yeah, now it makes sense. Yeah, it was this one. Exactly, it was this one, then I changed it. Yeah, okay, now it's fine.
Yeah, so yeah, 1-1, there's
Sense.
very little overlap.
Yeah, thank you.